Okay, so that transforms the physical view of conservation written in an integral form into a differential equation. Okay, so that's what I'm going to write down over here. The differential equation is partial rho partial t plus the divergence of f as a function of rho is equal to the source term as a function of rho. This is called the conservative form. It is directly derived from the physical conservation statement. Okay, another thing you can see is that if the space is just one-dimensional, so let's say take a one-dimensional special case. What is divergence in one dimension? It's just the derivative, right? A vector in one dimension is just a scalar, right? And the divergence in one dimension is just the spatial derivative. So in 1D, it's just a partial f of rho partial x is equal to s of rho. So that's what happens in 1D. And from the 1D analog, you can see immediately how we can write the same equation in the so-called primitive form. That is taking a chain rule. So we basically write partial f partial x. Instead of a spatial derivative of x, we want to express it as a spatial derivative of rho itself. So we get here partial f, well, actually in 1D df d rho times partial rho partial x. Right, this is the primitive form. And in multiple dimensions, the primitive form is this thing times partial f partial rho. Now because rho, df d rho, dot product with the gradient of rho is equal to s. So df d rho is a vector because f has many components, right? And that dotted with the gradient of rho becomes the same as that term. And we also have integral form. That is just the form we started with. That is the ddt of integral of rho dx plus the integral over the boundary of no gradient, boundary of f dot n ds is equal to integration of s dx. Okay, so these are the three forms of a conservation law. Any conservation law should be able to be written into any of these three forms. And we are going to see these three forms are very useful in both analysis and constructing numerical schemes for these conservation laws. Examples of conservation laws. So the simplest example of a conservation law is this. Well, have we seen this equation before? Yes, thank you. That means you've seen this equation before, right? So it's the linear advancing equation we have been playing with in finite difference. Is that a conservation law? It is. What is f of u? 1? F of u is just equal to u because this is f of u, right? This is where f of u should be. So f of u equal to u means it's advection equation. How about the more general form with the constant u here, is that a conservation law? If it is, what is f of u? It's big U times U, because this is a constant. You can just move it into the derivative. All right. Now a more interesting case is, what if, so this big U is the speed of advection, right? It's like how fast the wave goes. If big U is negative, the wave goes backwards towards the left. If U is positive, it goes towards the right. What if this speed of advection actually depends on the solution? Actually, what if it is the solution? What if it's small u times du dx? Is that a conservation law? Yes. What is f of u in that case? U square? U square over 2, yes. That is because if f of u is equal to this, then partial f of u, partial x, is partial u square over 2 partial x. That is u times partial u partial x. That's exactly what we have. And this has a name, is Burger's equation. And sticking with our scalar conservation laws in simple equations like that, we also have this so-called Berkeley-Leverett equation. The form is actually, I've seen several forms of the Berkeley-Leverett equation, but a general thing about this, the Berkeley-Leverett equation, is that the u has to lie between 0 and 1, and f depends on u in a very interesting way. Depends on u like that. So it's almost like a bimodal function, or something like a logistic function. This equation models the flow of oil and water in a porous media, and has been widely used in petroleum engineering. The u here lies between 0 and 1, describes the fraction of water in the flow. The other fraction is oil. And f represents the flux of water. So when the fraction is 0, of course the flux is 0. There is no water moving through. And when the fraction is 1, it's all water, so it's all water moving through. But in the middle, because of the complex dynamics involving surface tension and the porous media flow, the flux behaves in a very interesting way. That's where this thing comes from. The nonlinearity comes from. This is another good example of scalar conservation law.